Thank you, Romy. Thank you, Mike. Apologies for not being present in San Diego at the moment, but let's proceed with a report out from the experiences and learnings from the structure refinement activities that we undertook for the D3R Grand Challenge 2. So the outline of my presentation, my brief presentation, is shown here. I'll provide you with a few key figures for the PDB, and then talk about the group deposition system that we developed to support D3R, and then go through the structure refinement protocol, talk about the experience and learnings from the Grand Challenge 2, and then provide some acknowledgements. So very briefly, the Protein Data Bank was the first open access digital data resource in all of biology. It was established, as many of you know, back in '71 with only 7 X-ray structures. Today, it's the single global archive for experimental macromolecular 3D structures, and it's managed by the Worldwide Protein Data Bank Partnership, which includes regional data centers in the US, that's the RCSB PDB Europe, that's PDB Europe, PDB Japan in Asia, and Biomag ResBank provides some services related to the archiving of NMR experimental information. Some facts and figures about the PDB, just to impress you. The number of structures available today exceeds 128,000. In 2016, we managed somewhere on the order of 11,500 new depositions. We're supporting a total depositor population worldwide of about 30,000, and we have well over 1 million unique users coming to the various PDB sites worldwide. Collectively, from the 3 FTP sites that are maintained, there are more than 500 million data file downloads per year. That's on the order of 1.5 million per day. As I mentioned, the US Protein Data Bank is headquartered at RCSB PDB at Rutgers and UCSD, and fully 70% of the global PDB usage goes through the combination of Rutgers and UCSD. The group deposition system was recently developed by RCSB PDB to support batch deposition and validation of related structures. So these are structures that fall into a group of some kind. This was originally developed to support the D3R blind challenges with large data sets coming in from industry. Thank you very much for all of you who are supporting us. But we've found a lot of customers for the group deposition system outside the context of the D3R challenges and even outside academia, with more than 1,300 structures deposited through the system to date, with anywhere from about 10 to literally hundreds of structures per group. The way group dep works is that it sits alongside the global Worldwide Protein Data Bank one dep deposition, biocuration, and validation system, and a user brings multiple data sets to the front end of group dep. They are processed and then uploaded into the one dep system, so they get the full benefit of all the WWPDB validation and biocuration activities, and then are made available for loading into the PDB database and ultimate release. I want to emphasize the fact that group dep takes full advantage of all of the machinery from one dep, and subjects any structure going through the group dep system to exactly the same deposition, biocuration, and validation that every other structure undergoes on a one-at-a-time basis coming through the one dep system. The D3R refinement protocol is depicted here schematically. We begin with data files from our contributors. The structure refinement is finished off, and then when the structures are in a state of sufficiently good repair to actually put into the WWPDB validation system, they go through group dep. If the validation is okay, they pass through to generate a D3R quality report. If not, they're subject to further refinement of both the protein and the ligand structure. Once the structures have passed through validation and the D3R validation report is prepared, there's a quality assurance check. If there's a fail at this point, we go around the loop again. If there's a pass, then the structures are provided to the challenge participants and also made available to the contributors for their final review. The structures are then held within the PDB and only released after the challenge has concluded. So an important point here that I want to re-emphasize is the validation of all the refined structures by the standard WWPDB script, and also the fact that the contributors, along with the D3R team, are classified as co-authors on the final PDB deposition. The D3R refinement protocol per se is depicted here in a little bit more detail. The structure factor files, the model files, and the ligand restraints come into the process. We use in parallel RefMac, Phoenix, and Buster, do electron density map review, and then go through the WWPDB validation system and make adjustments as needed. And once the system passes through the validation, then the structures are made available both for the D3R team and ultimately, of course, for the challenges, and then PDB release. I don't know why I'm having difficulty advancing the slides, but let me see if I can.
Are you? Is your mouse actually? Can you click back on your PowerPoint window?
There we go. Thank you. So the focus of the D3R challenge number 2 were the FXR data sets from Roche. Thank you very much. In all, we refined 36 co-crystal structures and 1 APO with resolution limits ranging from 2.6 to 1.7 angstroms. You can see that there were 3 different point groups and 5 different space groups in terms of the crystal systems, and the molecular weights of the asymmetric units varied from monomer up to from a single protein up to 4 proteins. Ligand molecular weights varied anywhere between about 220 and more than 500 Daltons. 3 of the ligands contained bromines. 4 of the ligands exhibited alternate conformations. All ligands are buried in the binding pocket that's characteristic of the ligand binding domains of the nuclear hormone receptors, of which FXR is obviously a member. The refinement that was done here in New Jersey by Wanwan Yang and Chenghua Xiao showed improvement in the quality of the protein structure itself. So you can see in this table a variety of quality statistics for each structure that rest principally on the quality of the protein, not the ligand, and see both the initial and the final ranges and the average change. And with the exception of the RMS z-score for bonds and the RMS z-score for angles, everything else got better. So in a sense, what was done was to slightly relax the geometry, but ever so slightly to relax the geometry to provide for better values elsewhere in terms of the outcome of the refinement. I point you in particular to the improvements in clash score that we saw, where there were actually quite significant number of clashes in some of the initial structures, which were dramatically reduced as a result of the refinement. Similar benefits were obtained in terms of outliers for side chain rotamers, as you can see in this line of the table. We have an overall quality statistic, which we recently published in Structure. This is Xiao et al. That I commend to you, and we saw overall qualities ranging from 0%, meaning among the worst in the when compared to the entire PDB archive, up to the 70th percentile, and we were able to shift these to 5, in the range between 5 and 80th percentile, showing an improvement of about 25 percentile points on average across the structures. Moving on to ligands, we saw modest improvements in the real space R factor. In fact, improvements all around: real space R factor, real space correlation coefficients, significant reduction in the number of outliers in terms of bond lengths and bond angles, reduction in clashes, improvement in the z-score and RMS bonds and RMS, and the z-score and RMS angles. And we also saw a more balanced outcome in terms of the RSZD plus and RSZD minus. These are two statistics statistical measures of ligand quality that were developed by Ian Tickle at Aztec Pharmaceuticals. So our method for generating the ligand restraints went through, unfortunately, quite a bit of trial and error, as some of you may have seen. We generated restraints with both the AM1 and RM1 semi-empirical quantum mechanical optimizers, with and without reference values coming from MOGL, which comes from the Cambridge Structural Database that's managed by CCDC. And we found that we had to vary the planarity settings in order to get 6-membered rings, aromatic groups that were in fact planar and appropriate looking side groups projecting from those aromatic systems. The very best results that we obtained across the entire set of structures were with AM1, including the MOGL ideal values, with tighter planarity than would be the default in Phoenix. And in some cases, we had to manually set some of the restraints in order to achieve the planarity that was wanted. One weakness, though, we did see of AM1 is that in at least one case, we saw a discrepancy between the planarity targets that were generated by AM1 and RM1, and had to go in and actually manually correct those in the case of 1Y-MRC in order to get the chemically sensible arrangement, and one that also matched the appearance of the electron density maps. So in terms of learning, we saw partial disorder and alternative conformers in some cases, and here's one such example. This is the structure 1DQZC, which was obtained at about 2 angstrom resolution, where you can see that the position of the cyclohexane is not first not defined as a single site because of because of torsional flexibility, torsional freedom about that bond. And we also saw that there was some rotational disorder in the cyclohexane. Moving on, there were also cases where we saw evidence of the entire ligand being present in the binding site in the protein in 2 distinct orientations, as depicted here with 1TXCA. The best interpretation of the difference electron density map, showed here in blue, suggests that there are actually 2 distinct conformations of the ligand, with the bulk of the differences being reflected in this part of the cross-shaped structure. We also had some difficulties in the cases where there was a bromine in the ligand. This is something that I had seen before multiple times at SGX Pharmaceuticals, where we saw the bond between the bromine and the carbon atom broken by the X-ray beam during the course of the X-ray experiment. As a consequence, what you're really seeing in the crystal is 2 ligand species, one with and one without the bromine. The way we dealt with that was to model subtle. So and these 2 ligand species occupy 2 slightly different positions. The way we dealt with this, imperfectly, I admit, is to modeled the bromine with reduced occupancy. And you can see the results of difference Fourier calculations here with treating the bromine occupancy as 1 versus 0.5. And our best guess in terms of the outcome of the crystallographic experiment is in this particular case that the bromine occupancy was about 1/2. And what we're actually looking at is a superposition of 2 states of the ligand in slightly different binding poses with one with and one without the bromine, of course. We weren't able to do any better than this, and my advice in the future would be to avoid including ligands with bromines for the purpose of these challenges to eliminate the ambiguity that occurs when you have these 2 species in the crystal. The other thing that many of us are aware of course, is that there's ambiguity in the electron density maps. This particular example is depicted here. It's not from the FXR study. It's from a different study that was done here at Rutgers. And what you can see is that this is a quasi-symmetric ligand. Using the electron density alone, it's not possible to determine which is the correct orientation about this freely rotatable bond until you realize that in terms of the hydrogen bond neighbor, that it's very unlikely that there's a methyl group, and in fact more likely that there's an oxygen in this. And try and ensure that we had the best possible pose selected in terms of maximizing the hydrogen bonding of the ligand and avoiding potential nonsensical outcomes such as the one that's depicted in this example. Before I close, I do want to make the point that protein crystallography is not a high precision method in the same way that small molecule X-ray crystallography is. My rule of thumb for working with protein crystal structures is that the precision of the atomic positions of the non-hydrogen atoms is about 1/10 of the resolution limit. So perturbations on the order of a few tenths of an angstrom from ideal values in the electron density maps are to be expected because of the relatively low precision of the method. At 2 angstroms, I'm suggesting that the precision of the atomic coordinates for the non-hydrogen atoms is on the order of 0.2 angstroms. And so any attempt to try to dock a pose with respect to the X-ray rendition of truth, where the deviations are smaller than a few tenths of an angstrom, are probably not meaningful because of the relative lack of precision of protein crystallography versus small molecule crystal structures. Small molecule crystal structures have precision of bond lengths and bond angles on the order of 1/100th of an angstrom or 0.1 degrees, which is significantly higher than the precision of the 3D structures that come from protein crystallography, particularly of the non-covalently bound ligands, which we're fitting into electron density difference features, such as the one depicted here. So with that philosophical note, I want to thank all of the people who were involved on the Rutgers side in making this happen. The bulk of the work was done by Wanwang Yang and Chenghua Xiao. Zukang Feng was the developer of the group depth system, and supervision of various aspects of the project were provided not only by myself, but John Westbrook, Jasmine Young, and Ezra Pasak. I also want to acknowledge the important roles that Simon Gathiaka and Shuai Liu in San Diego played in helping to evaluate the quality of the refined structures, and of course Mike and finally the principal investigator Romy for inviting us to be part of the D3R project, which is not only helping to advance the cause in terms of improving methods, but is also helping to advance the cause in terms of bringing structures that would be otherwise locked in company databases out into the public domain and ultimately available to everybody to use for methods development, etc., from the Protein Data Bank. So thank you from everybody here at Rutgers and also the team at the PDB team at UCSD. As I introduced in my opening slide, we're part of the Worldwide Protein Data Bank Partnership, which includes PDB in Europe, PDB Japan, and BMRB, and we are funded by NSF, NIH, and the US Department of Energy for our core operations, which of course support all the activities involved in PDB data deposition and PDB data distribution. So happy to take any questions, defend the hypothesis, etc. Thank you.